Assalamualaikum and good day. My name is Siti Nurikisani. In this presentation, I will explain the structure and operation of P-channel MOSFET, also known as Pmos. I will discuss the role of the gate, source, and drain terminals and explain how the gate voltage controls the current flow through the device. And also, I will share some applications of Pmos in this video. So, what is Pmos? A P-channel MOSFET or Pmos is a type of a field effect transistor where holes act as the majority charge carriers. It is widely used in CMOS technology together with NMOS transistors to create low-power digital circuits. Unlike bipolar transistors, a Pmos is voltage controlled, meaning the current flow is controlled by the gate voltage, not by the current. This slide shows the basic structure of a Pmos. So the device is built on an N-type substrate, and then the source and the drain are heavily doped P-type regions. On top of the substrate, there is a gate terminal which is separated from the semiconductor by a thin silicon dioxide insulating layer. So this oxide layer is very important because it prevents direct current flow into the gate, and then allowing the gate to control the device using an electric field. So as a result, Pmos devices have very low power consumption. So each terminal in a Pmos has specific role. First, the gate controls the formation of the conducting channel by applying an electric field. So ideally, no current flows into the gate. And then the source supplies holes, which are the charge carrier in a Pmos, and it is usually connected to a higher voltage. And last, the drain collects the hole and current flows from the source to the drain when the device is turned on. Okay, so now let's look at how a Pmos operates in the off and on states. On the left, we see that the Pmos in the off state. So here the gate voltage is equal to the source voltage. So no conducting channel is formed between the source and drain. As a result, no current flows through the device. So we notice that the P plus source and P plus drain regions remain, but the channel under the gate is absent. While on the right, the Pmos is in the on state. So when the gate voltage becomes more negative than the source, a P-type channel forms beneath the gate. And then this will allow holes to flow from the source to the drain, creating a current. You can see the channel highlighted, so connecting the source and drain regions. So to summarize, the Pmos is off when the gate is at source voltage and on when the gate is more negative than the source. So this demonstrates how the gate voltage controls the current flow in the Pmos transistor. And then the amount of current flowing through the Pmos depends on the gate voltage. As the gate voltage becomes more negative, the channels become stronger and the drain current increases. So this shows that the Pmos is a voltage controlled device where the gate voltage directly controls the current flow. So these are some examples of applications of Pmos. So the first diagram shows the CMOS inverter where the Pmos transistor is used as a pull-up device. And then the second diagram shows a CMOS NAND gate, which in this circuit, multiple Pmos transistors form a pull-up network. And the third diagram shows a Pmos current mirror, which is commonly used in analog circuits as a current source. So these examples show that Pmos transistors are widely used in both digital and analog electronic circuits. So in conclusion, the Pmos is a key building block in modern electronics. It is a voltage control device where the majority carriers are holes. The current between the source and drain is determined by the gate voltage. Where the gate voltage is more negative than the source, a P-type conducting channel forms, turning the device on. But when the gate voltage equals the source voltage, the channel disappears and the device is off. And then the structure of Pmos consists of P plus source and drain regions, an N-type substrate, and a gate terminal separated by an oxide layer. This design allows the transistor to be efficient and low power since the gate draws almost no current. So in practical applications, Pmos transistors are widely used in digital circuits such as CMOS inverters and logic gates where they act as pull-up devices, and they are also used in analog circuits, for example in current mirrors and active loads. This demonstrates the versatility of Pmos devices across different types of circuits. So overall, understanding the structure, operation, and applications of Pmos transistor is essential for designing efficient and reliable integrated circuits, especially in CMOS technology, where they work in combination with NMOS transistors to minimize the power consumption. Alright, so that's all from me. Thank you for listening. Bye.